if you remember, what we saw last week was this thing that we called, what did we call? A direct geometric model. Nice. Which shows us what? How is the end effector oriented and positioned? So what is the pose of the end effector of the robot? If I know the joint variables. So what is the position of each joint, right? And we saw a simple method for coming up with this direct geometric model. Today we'll see a more general and more used in the world of robotics method, and it's a little bit more complicated, but it's gonna be interesting, I hope. So the Denavit Hartenberg convention. Bit of background, again, what we saw last week, we talked about these revolute joints. Remember, they're called revolute, not rotational. We talked about prismatic joints, which allow translation in 1 degree. And that usually when we add joints, we get extra degrees of freedom. Not always, sometimes, depends. And we talked about this concept of the work envelope of the robot. So the area that the robot can reach with its end effector. And we defined this thing called the direct geometric model. How did we do it? We used the concept from 2 weeks ago, the transformation matrices, where we saw that we can break down a complicated transformation from the base to the end effector. We can break it down into smaller parts and more fundamental, more easy, based on rotations and simple translations. And we define like the overall one by combining all of them with multiplication. Okay, so this is the direct geometric model. It's basically a 4x4 transformation matrix, which shows us what is the position and orientation, or what we call pose, if we know the lengths and the values for the joints. Okay? So today we talk about this Denavit Hartenberg convention. It was introduced by these two guys, Denavit and Hartenberg. It was initially for another field of studies, similar but not robotics. It was later on used in robotics and it was proven very useful, around 81, I think. And basically what it does, it standardizes the way we describe robots, and not necessarily the whole robot, but it starts by defining as a fundamental unit the link of a robot. So the thing between the two joints. Okay? And it describes each link using only 5 parameters, regardless of how it looks, what shape it has, you know, how the joints are oriented, what kind of joints we have, and so on and so forth. Okay? It can be used on any kinematic chain or any robot. Oops. And the result is a direct geometric model. Basically, by defining these 4 parameters for each link, we can combine all these parameters to define a direct geometric model from the base of the robot until the end effector. Now, why do we need a more complicated method than what we saw last week? Basically, this was easy to solve last week with what we saw with simple transformations, if you remember, writing on the board and so on. But robots might have like more complicated forms. This is like a very famous robot from KUKA, where they don't have like a straight uniform, the links don't have a straight uniform shape, and there we might need like a bit more complex way of thinking for defining, okay, what is the transformation from this joint to the next one? Is it just the rotation and translation? Is it first the translation, then rotation, and all these things? Okay, so we standardize this, and we define this convention. Another example you can see here, for instance, we have one joint here. This is the same drawing. This is the top view, this is the side view. And for instance, we have this joint here with the blue line rotating around this axis, and then we have another joint position arbitrarily. It has, you know, it's higher, it's you can think of transformations from here to here, but it's better if it's something standardized, okay? Now, before we move on to explain the convention, I want to see one more example with 3D robots and make sure we understand how these drawings work. Okay, and once we do, then we will understand. We'll start talking about the convention. So I use this kind of drawings for the course and also for the exam, so it's good if it's clear for everybody what's going on here. Okay, so what do we have here? It's a representation of a robot. We have, first of all, we have a fixed frame, okay, X and Z. We'll stop using Y so much, because if we know X and Z, where's their position and oriented, we can automatically define Y. And because we're going to use like a lot of axes in our drawings, then the less lines we have to draw, the cleaner the drawing will be, okay? But if I know X and Z, where should Y point? Towards U, right? So if X points there, Z points up, then Y should point towards the inside, right? Sorry. So X, Y, Z. Okay? I told you not to forget your right hands. But we don't really use it at all for our calculations. It doesn't matter. Sorry, Y. But that's tough life. You should become more important. Okay, so what do we see here is the fixed frame, yeah, with the red lines, X and Z. And this is how I usually represent an axis, a joint that rotates around an axis, the vertical axis. Okay, with these two things that kind of show like it's rotating around this black line. Okay, and then I use this arrow as well to show you, okay, this is a rotation and the variable of the rotation. So this is the angle, okay, which we call Q1 because it refers to the first joint. Yeah. Then here we have an element, a link, connecting this joint with this joint. Okay, and this link has a length. The length is L1. Yes, clear until now. What do we have here? What do we say I usually represent with a diagonal line? A what? It's not Y, it's an axis. I didn't give it a name. Okay, just to be clear. It's an axis, points towards, it's aligned with a, yeah, it's perpendicular to the slide. Okay, it doesn't have a direction yet. It's just an axis of rotation. Okay, of this joint here. So it rotates like this somehow. The axis points towards you or in the board. Okay, and the angle of the axis is Q2. Right? Now, if you remember, this is how I represent prismatic joints, so sliding, so it kind of shows like it slides along this element here, okay, along this link. And you can also understand it's a prismatic joint, it's sliding because here the distance is a variable. So the distance from here to here, okay? Or you could have said that it's the distance from here to here is variable, and from here to here is fixed. And I don't know, from here to here you have Q3. I think I can draw. Yes, I can draw. So from here to here is Q3. And from here to here is QL4. I don't know. I can draw, but I think I should better not draw because it's ugly. Okay, and here is Q3. Yes. Okay. Doesn't matter how you put it, it's the same thing. Okay. And what do we have here? This is another joint which rotates around an axis which is horizontal. Okay, along this direction. So it's basically an axis that rotates like this. And you can see it has another final link here with L3. So basically, this L3 points downwards now as it is on the paper, but I can rotate it along this axis. Okay. Basically, the first one is this rotation. Okay, my waist. This is the second one. Okay, the third one is a translation. I cannot not rotate my angle, but yeah. And the fourth one is a rotation in this direction, right? This is because we're going to use these drawings quite a lot for examples, so it's better if it's clear to everyone. Now, we said Denavit Hartenberg convention, we said 4 parameters, right? What are these 4 parameters? Basically, it's 2 distances and 2 angles. Okay? And we give them names as well, call it the joint offset and the joint angle, or the link and the link length and the link twist. Okay? And by convention, we use these 4 letters to describe them: D, theta, R, and alpha. So this is meant to be an alpha. It's not a typo. In some textbooks or at Wikipedia, this sometimes is called A. The link length is called A. But for people like me, it's easier if we use a different letter and not confuse A with alphas. Safer. In more modern textbooks, they use R as well because they notice that it's confusing. Okay? Now, how are these parameters defined? Basically, when we have joints on a robot, we always look from one joint to the next one. Okay, these 4 parameters describe the situation from one joint to the next joint. Okay? So if I can figure out what's the transformation from joint 1 to joint 2, and from joint 2 to joint 3, and from 3 to 4, then I know how to combine them to figure out what's the overall transformation, right? Okay? And these 4 parameters, they always relate, yeah. When I say I want to calculate DI, let's say D1, and I'm talking about this joint offset from joint 1 to joint 2. Okay? The angle from joint 1 to joint 2, the length from joint 1 to joint 2, or whatever I have. Okay? So we use these indexes a lot. So yeah, with this convention, we always go from current one to the next one. And you can see here also a visual example before we talk exactly what's going on here. So I have some links. So the green link and the purple link I minus 1 and link I. And these links connect joints. Like that's what we saw yesterday. Okay, so here I have one joint, which has an axis of rotation. Let's call it joint I minus 1. Here I have another joint, joint I. Here I have another joint, I plus 1. Okay, so you can imagine that your robot has something before here, and here you have a rotation. Then you have some link which has some kind of shape. We don't care what it is. And then it has another link, another joint, sorry. And you can imagine that these 2 elements, the green and the purple one, they can rotate relative to each other along this axis, right? And another link and so on. You can add as many as you want. Okay? And the idea is, I want to define some coordinate frames on each joint and describe the transformation between subsequent coordinate frames. Between coordinate frame, let's say for joint I minus 1, coordinate frame I minus 1, and I. Okay? And I break this down into 4 transformations. 4 parameters, 4 elementary transformations. So, and we said that 2 parameters relate to distance and 2 parameters relate to angles. Therefore, what do you expect to have? What kind of transformations? If 2 are for distance and 2 are for angles, I'll have 2 rotations and 2 translations. So basically what this guy showed is that any coordinate frames arbitrarily positioned between each other, they can be reached starting from one going to the other. It can be reached using 2 translations and 2 rotations along some axis. So we define these 4 transformations. We saw last week and the week before we use these transformation matrices. And we have basically one set of transformations, which is a combination of rotation and translation. What happens first? A rotation or translation? Okay, neither. Doesn't matter. There is no concept of what happens first or next. It's 2 different ways of seeing the same thing, right? And I have another set of transformations, another set of rotation and translation. As you see, the first 2 transformations relate to the x-axis, so it's a rotation and translation along the x-axis. Okay, and the second one is a rotation and translation along the z-axis. Okay? And which happens first, the transformation around the x or around the z? Doesn't matter. Now, if I combine all these 4 together, I know the form of these ones, right? You remember, the rotation around x is this transformation 4 by 4 with has like zeros for the position and 1, 0, 0 in the first row and first column, and then some cosine sinus, right? So if I do these multiplications all together, these 4 ones, I will end up with a general transformation matrix, which here, excuse me, you see the parameters that we talked about, theta, alpha, d, and r should appear somewhere. I might have a typo here. Okay, and that defines the transformation from joint I to joint I plus 1. That's the idea. By combining from 0 to 1, from 1 to 2, and from n minus 1 to n, multiplying all together, I get the overall transformation from 0 to 1, from 0 to the n effector, which is my direct geometric model. Now, how do we do this? Let's go into more practical stuff, because I keep on talking for 10 minutes now. There is like a indrumatore, like a step-by-step method that we use in order to define these parameters and make sure we don't make any mistake. Now, it's very specific, so if you follow it step by step, you're not going to make any mistake. If you don't follow it step by step, then you will make a mistake, probably. But we get a lot of practice. Also in the labs, you practice it, so we're sure you don't make any mistake. So the first idea, and I have actually some examples, so we're first going to talk about this and then do like 2 or 3 examples so it gets more and more clear. Okay? So the first thing that we need to do is identify what are the axes, what are the joints of the robot. Okay, I'm not drawing a robot yet. Bear with me. Okay, and then, as we said, we put a coordinate frame on each joint. Okay, and we start by putting the z-axis. We define the z-axis. How do we define it? Along the axis of rotation or translation. I might have revolute joints, I might have prismatic joints. For each of these joints, I just put a z-axis along the direction where it rotates. Okay, so here, for instance, the first joint, direction around which it rotates is this axis pointing upwards, right? So I would put a z1 there. Then the next step is we have like z1, z2, z3 for joint 1, joint 2, joint 3. I go and define a thing that is called the common perpendicular between subsequent z-axis. So I find the common perpendicular between z1 and z2, between z2 and z3, between z3 and z4. Okay. what does this common perpendicular mean? And can we always find it? What common perpendicular means? A line that is perpendicular to all the things that we're talking about, okay? So if I'm talking about two axes, because I'm talking about subsequent z-axis, z1, z2, I'm looking for a line that is perpendicular to z1 and z2, for instance, okay? Can I always have a perpendicular on two lines? Very direct. Yes? Always, always? Are you very sure? Okay, good. Good that you're sure. You can always have at least one line that is perpendicular to two other lines in three dimensions. Sorry. Okay, and let's try to see some examples. Like for instance, I'll take like big visual lines. I have a line that is aligned with the floor here at the corner, right? And I have another line that is aligned with the ceiling there in the corner, right? What would be perpendicular to both of these two lines? So it's like something like this and something like this, right? That line there is perpendicular to this one, hopefully, if the constructor was careful, and it's also perpendicular to that line, right? You can think of weird configurations. Basically, however they are oriented, you will always have like, I don't know, something like this and this. It would be something like this. Okay? Doesn't matter, you always have at least one. Are there cases where you can have more than one? Okay, what case? When I have parallel. Then all the lines here, they are, I don't know, between that line and that line, all the lines from here to there, they are perpendicular to each other, right? Okay, great. Well, we always have at least one. There is also another case, which is like a special case of the parallel when they're collinear. Okay, then I have even more infinite. So it's like, if they're parallel, then I have infinite axes. If they're collinear, I have twice as infinite. Because they can also be oriented, however, almost. Okay? Good. So that's the second step. The first step, we put z-axis at every axis, every joint of the robot. Second one is I find perpendicular between subsequent axes. Okay, between z1, z2, z2, z3, z3, z4. And we put the x-axis of the ith joint aligned with a common perpendicular between the zi and zi plus 1. So x1 would be perpendicular between, will be aligned on the common perpendicular between z1 and z2. x2 will be aligned with the common perpendicular of z2 and z3. Okay? Now that satisfies two conditions. Because the xi is on the common perpendicular between zi and zi plus 1, this means that xi will be perpendicular with zi, which it should be, because it's a coordinate frame, right? And all the axes have to be perpendicular. And it will also be perpendicular to zi plus 1. We'll see how is that important later on. And as a convention, the z-axis, the positive direction, we choose ourselves, but for the x-axis, we choose the direction going from z1 to z2, from z2 to z3. Okay, that's a convention. We could have chosen differently, it wouldn't have changed much. Let's see one example, because I like to draw. Let's say I have I'll draw a robot. Yeah. Or two links. Actually. So this is my one link. It's difficult to draw in 3D, but we'll try. So this is one joint, this is the second joint, and here I have another element, whatever. What did we say is the first step? First step, align Z with each coordinate of each coordinate frame. So let's also give them names. Let's call this I. Let's call this I plus 1. Okay. And we align the Z axis of the first coordinate frame, let's say, with of the ith coordinate frame with the axis of rotation or translation of each joint. Okay. So what is the axis of rotation here? It's this line here. So I will say this is my Z. Okay. An important thing to remember is that axes don't stop. Okay, they go to infinity both ways. Where is the zero at the moment is not important. It will be defined in a second. Okay, and I do the same for the second one. So this will be my Z I. This will be my Z I plus 1. Okay. Good. And I do this for all the joints from 0 to the end. Next step, identify the common perpendicular between subsequent Z axes. Now here it's difficult to explain how the axes look, but let's say this is pointing a bit outwards and this points a bit inwards. Okay, difficult to imagine. I have some drawings, some videos, so it will become a bit easier, but let's say they look like this. So I don't know, the common perpendicular is something like this, where here it's perpendicular and here it's perpendicular. Doesn't look like that because it's 2D, but imagine that this goes like this somehow and this goes like this, and then the line that is perpendicular to both. Okay, what's the next step? They align the x axis. Okay, now I only defined the common perpendicular between I and I plus 1. If I had an I plus 2 there, I would have done the same thing, yeah? So which axis would be aligned with this common perpendicular? x1, xi, sorry, yeah? Great. And if we want, having z and x, I can define yi as well, but don't care about the Greeks. The y's. So once we have identified these coordinate frames, we start working on identifying the 4 parameters. 4 axis I, from I to I plus 1. Okay. So first thing, Ri is the distance between Zi and Zi plus 1 as measured on xi. Okay. So I have Zi, I have Zi plus 1. I want the distance, but along this direction. Okay. So this distance here. This will be the Ri. Okay. In this case, where I have this perpendicular, this Zi and that Zi plus 1, the distance would be the length of this common perpendicular, right? Along the xi. Okay? Then I have alpha I, which is the angle between Zi and Zi plus 1. Okay? Around xi. Now, the distance is easier to understand why is here, because distance between two arbitrary lines is basically the length of the perpendicular line. Okay, but the angle along this direction, what is this? Basically, if I have these two lines and I have the perpendicular here, it's going to be the angle that I would need to rotate one of the two lines in order for them to be parallel, but rotating around this common perpendicular. Okay? Let's say I have, should use bigger stuff. Yeah, I have these two. Okay? These two lines. Better. These two lines. Then if I bring them close together, it's this angle. Okay? It's, what do you mean smaller or bigger? So I have Zi plus 1. Okay, very good question. It's basically the angle starting from Zi and going to Zi plus 1 along xi. That says everything. Let's analyze and break it down. I have Zi, and I have Zi plus 1. And I have xi pointing towards you, right? So in this case, it will be this one rotating until they are aligned. So it would be the small angle, let's say. Okay? In this case, this one rotating until this one, again the small angle. Doesn't have to do with small or big, basically, but yeah. It has to do more with whether it's positive or negative. Okay? Is this angle here, whether it's small or big? One small detail, let's consider that both of these axes point upwards in this end. Okay? Because they have to be aligned and pointing in the same direction. Okay, that's why it's this angle and not this angle, because then they point inverse. Okay? Yeah? Now, is this rotation, is this angle positive or negative? So remember, Zi plus 1, and xi points towards you. Why? The role of the right hand says. Okay, so same angle. Is this positive or negative? Okay, now is it positive or negative? Okay, I follow too. I failed to follow your logic. So you're saying the rule of the right hand. What does the rule of the right hand tell me? There are two rules. They're kind of the same rule, but yeah, we saw two variants. I'm talking about that rule. And what does the thumb show me? Yes, exactly. So I said Z1, Z2, and X pointing toward you, right? So this rotation, it points towards the negative part of the X-axis, right? So it's negative. Yeah? I heard positive. Sorry. Anyway, doesn't matter who is wrong or is right. The point is to understand. Okay, and how do we define these things? So, Z1 pointing up, Z2 pointing to your right, and X1 pointing towards you. This would give me a negative rotation. Starting from here, starting from Zi, going to Zi plus 1, along Xi plus 1. It's a negative rotation in this case. Okay? Or it could be a positive rotation, but it would be like, whoop, this much. which is the same thing. We'll see more examples. Stick with me. But everything is defined by the rule of the right hand, and with that little detail there. Angle between zi plus 1, so going from zi to zi plus 1 along xi. If your xi points towards you, this rotation is negative. If the x-axis points towards me, this rotation is positive. So of course it depends how the x-axis it's pointing, okay? But that's why we say around xi, because the direction of xi defines also the sign, if it's positive or negative. Okay? Good. So first, this distance, okay, the distance between the two vectors, then the angle between them. Okay? Next parameter. Okay, I need to draw another axis. Let's say here I have another axis. Okay, and this gives me zi plus 2. So I have, blue. So I have xi plus 1. Okay. So then I have di, the distance between xi and xi plus 1, along which axis? Along the zi plus 1. So this distance. Okay, this is my di. Basically. Okay. So from here to here, distance along xi. From here to here, distance along zi plus 1. This is zi plus 1. And then finally, theta is the angle between xi and xi plus 1. So this xi and this xi plus 1 around zi plus 1. So if I extend this one, okay, I can consider it here. Okay, I just extend it. And then this down here, there is like an angle between them. Or this up here. So this is xi translated up there. Okay. Shall we try to visualize this? Yes. Yes. Well, your robot will end with an end effector, right? So what we do, we'll see that at the end, we put a coordinate frame at the end effector the way we like it. Okay? So that means I will have a z at the end effector, so I can define the final x. Okay? Usually the end effector, we position the coordinate frame the way we like, because we have a tool there that has its own reference frame or something like this. Okay? But that's the idea, is that at the end there will be an end effector, a tool, and then we put the coordinate frame how we like, and based on that we calculate. Okay? Shall we visualize this a bit better? Let's try at least. So let me pause this. Yeah, forgot how this works. So, hey, I have two coordinate frames. One here, one here. No, you don't see it. Okay, now you see it. So one here, one here. Okay? And basically, how did I calculate these coordinate frames? I have two axes, two joints. One here with the blue, and one here with this orange one. randomly oriented towards each other. So it's basically this and this, okay? And I want to show that I can go from this one to this one using these two rotations and two translations. By doing first a rotation, first a translation rotation, then another rotation translation. Okay? So I start by doing the first translation. So I do this translation starting from here, going to here by this distance Ri. So I have this I'll write it here. So visible translation on which axis? X-axis by Ri. Okay? So it's this translation that we just saw. You see it? It just translates along the blue axis, which is the x. Okay? You see it, right? Yeah. Good. Then what was the other thing that we said that we do? We do a rotation around x. Okay, so rotation around x by alpha I. Right, so it's basically, what are we trying to do now? Align the two z's. What are the z's here? It's the two red ones. Okay, so then I do a rotation around z. You see? No, sorry, around x. I rotate around x. Now, do I rotate around this x or this x? Sorry? Here you are. This x or this x? It's the same. They're collinear because they just translate on x. Then if I rotate around this x, I will rotate like this. So here the order doesn't matter. Okay? But, yeah. Be careful if you change stuff. Nice. So then I do the rotation around x. Is this a positive or a negative rotation in this example? So I start from here and I go there. Negative? Positive? Nobody is positive about. You're positive about being negative. Why? Because I rotate, let's say if the axis is going towards downwards, and I rotate like this, okay? And if the axis shows me the positive, then my thumb shows the negative side, so it's a negative rotation, okay? Okay, so first translation, then rotation, and then what's next? What was the other parameter we saw? It's this distance here. So another translation and then a rotation. Okay, so I do let's see, translation of z, so I do this z by vi, so this distance here. Okay, and rotation on z by theta. Okay, so let's see. So I do the translation on z. Okay, you see I go from here, here, from here, here. Okay, and then I do a rotation around z. Zack. And I end up from the first frame to the second one with 4 transformations. Now, this last rotation, is it positive or negative? So I go from here, here. It's negative, right? From here to here. So the axis points upwards, and I move like this, and my thumb points in the positive direction, so it's a negative rotation. Is it positive or negative? So I start from here, rotate towards that direction. So it's a positive rotation because my thumb points to the positive direction. Don't let me fool you. Yeah, and you see the intermediate coordinate frames. So we start from here. After translation and rotation, we end up here. Then another translation and rotation here. Now, question. Let's be here. Okay, so I am there at this frame after these two. Right? Should I multiply this from the right or from the left? It was on the slides earlier, but I guess you don't remember yet. Y to the right or Y to the left? Who says to the left? Why?
Because it's the reverse of the comparison to the translation things, the notation, the translation.
Okay. Why on the left? If we multiply it from the right. So if we multiply from the right, then we're going to move along this axis, you're saying, right? Well, it's the other way around. If we multiply from the left, then we move along this axis. Because this is my fixed one in this case, right? If I multiply from the right, I'm going to move along this axis and rotate along this axis. Okay? Again, right-left multiplication. The thing is that you can learn these things by heart, or you can, see the slides, and during the exams you will have access to everything anyway. So, yes, it's an open book exam. But if you understand what's happening, it helps you avoid mistakes, common mistakes that you might do during the exams. Okay? So I don't ask you to remember this thing by heart. Okay, that we first do this, and then from the right we multiply the next two. But if you understand what it means, left and right multiplication, then you will not need to remember it. Okay? Or if you understand what it means, left-right multiplication and rule of the right hand and all these basic things, then during the exams with all the stress and, other exams happening and projects and you will have less chance of making mistakes. Okay, and that's what I want. Is this clear? Does it help visualize a bit some stuff? Okay. Good. Break. And then we do examples. 2 or 3 examples. So you get, because that's basically the whole concept. Unless you have questions. Do you have questions? Okay. Then let's take 10 minutes break. And we continue with examples.